All right, how's it going, everyone? Welcome to the Data Engineering Meetup here in Australia. We've got two really cool speakers from overseas today. Dave Bechberger, he's joining us all the way from Alaska, which is really cool, very fascinating place. An equally fascinating place, South Africa, where Archana is joining us from. So that's going to be really cool. She's doing a talk on data for machine learning, and Dave's going to be taking us through graph databases and Amazon Neptune. I think equally fascinating topics at the moment in the data engineering space. Just a few announcements before we get started. Obviously, our community conference, DataEng Bytes, is rapidly taking shape. So go check out our website if you haven't already. We've got our organizing team and committee up on our website. The CFP is live as well. So that's all ticking along well. And in the not too distant future, we'll be announcing how to get your tickets, both initially for the online component of the conference, but we're also planning to do an in-person component of the conference. So do stay tuned for that. So yeah, up first, or actually one other thing that I would like to mention is this on our Slack group for data engineering, there's a ton of jobs going on at the moment in data engineering. So definitely, if you're happy in your current role, absolutely continue going on with that, because I think, it's always good to enjoy that when you've got a really good role. But, if you're looking to get into data engineering, or, you've been a good few years in your role and just want to mix it up or something like that, definitely do check out the jobs channel in the Slack group, because just browsing through all of the jobs that are going on at the moment. I think there's never been a better time to be a data engineer. So definitely go check that out. Awesome. All right. Well, without further ado, our first speaker is Dave Bechberger. He's a senior graph architect, which sounds like a really cool job title, to be fair, at Amazon Web Services. He's going to do an introduction to graphs in general. He's written a book on graph databases, so I trust he's got some cool things, some good knowledge to share with us, and also going to take us through Amazon Neptune, which I believe is Amazon's managed graph database service. So that'll be really cool. He's also got a book to give away, one copy. So if you've got a really cool question for him today, I think he might be able to, you might be able to win a copy of that. And there's also a 35% discount code if you miss out. So either which way, you're going to win regardless. So stay tuned for that. Well, without further ado, I might add Dave to the stream. Tell us a little bit about yourself. How are you going there, Dave?
Hey, Peter. Thanks for having me here today. Yeah, really excited to kind of come today and talk with you all about graphs and graph databases. So maybe we'll kind of jump in and yeah, as you said, ask your questions in the comments, and best question can win a copy of my book here.
Sounds like the plan. Well, if you'd like to dive straight in, share your slides, we can get right underway if you like.
Sure.
Awesome. All right, I'm going to drop off. Take it away, Dave. Cheers.
All right. Thanks. Well, as Peter mentioned today, I'm going to be talking a little bit. I'm going to kind of start with an introduction to graphs and graph databases, and Amazon Neptune. But kind of before we get started, I wanted to talk a little bit about me. As Peter mentioned, I'm based out of Anchorage, Alaska, here in the United States. And I've been working in software for 20 plus years now. But what I really kind of found out that I really love to do is solve difficult distributed data problems. That's where kind of all the fun is. It's all the complexity of working with data, as well as all the complexity of building distributed systems. As he said, my current role is I'm working on the Amazon Neptune team as a senior graph architect, where it's kind of a very interesting role where I get to work, directly with customers, but also directly with the engineering teams, really kind of figuring out the best way to, solve customer problems using our technology. And as you mentioned, I am a co-author of the Manning book that came out last fall called Graph Databases in Action. So what are we going to talk about today? Well, what we're going to talk about today is we're going to start off, I'm not sure what everyone's, familiarity with graph databases is. So I kind of went, well, let's start at the beginning and talk a little bit about what a graph is, a little bit about why you use a graph, a little bit about what graph databases are, and then a little bit about how Amazon Neptune fits into those graph databases. And then, I don't want to spend too long on that. And then I'm going to kind of jump right into a couple of different demos that I have, and then, leave some time at the end for any sort of questions that you may have. So let's get started. What is a graph? Well, a graph at its very basis is a mathematical construct. But really what it comes down to is it's a way to model the data inside a domain based on the relationships in that domain, and to use those relationships and entities to explore connections and patterns in those connected data. I mean, the fundamentals of graphs and graph databases are really pretty simple. They're, the most fundamental, or one of the most fundamental elements is vertices. So vertices are nodes, depends on, but both of them are correct terminology. And really what vertices or nodes are, these represent the nouns in your domain, or the entities inside your whatever domain you're trying to model. The other main construct is that, edges, which represent the relationships between those those pieces of data. And kind of the actual final really piece of graph fundamentals that you need to know is that when you're working with graphs, at least most common graphs that you see used in terms of graph databases, edges have a direction, so they're known as directed graphs. So really what, when it comes down to what are graphs really about? Graphs are really about providing a way to intuitively represent data. Say, when you look at a graph and you look at, both the graph data structure or as graph inside it, whatever domain you're looking at, they tend to be very intuitive. And they're really easy to be able to represent connections between things. And those connections can get rather complex sometimes, and they can vary. Graphs are very good at showing these really complex, varied relationships and being able to use that to represent the world as it is. This tends to apply across domains. In the example you're seeing here, this is someone's family tree, a really kind of very simplistic graph data model, but it really applies across domains. It applies across domains like if you want to manage fraud, or you want to do identity management across different websites and different, to identify different unique users across many different devices, or something that's probably very relevant to a lot of what you guys work with in data engineering is being able to build knowledge graphs, or being able to connect data across different silos. So graphs tend to be very good at solving some very specific technical challenges that are difficult with other technologies. First one being combining data across data silos. Almost every business out there that I've ever seen, ever worked with, tends to have many different databases across many different systems. Maybe there's an e-commerce system and an inventory system and a warehousing system and a maybe a customer support system, and you want to be able to connect that data to get a holistic view of all of the interactions that customers had with a specific e-commerce site, for example. And graphs are very good at being able to pull those, or being able to connect those disparate data sources in a way that provides a quick and efficient way to look up those sorts of, to provide that sort of holistic view. They're really good at finding common connections and paths in data, or see how figuring out how how entity A is linked to entity B. This is the whole, you're probably familiar with the 6 degrees of Kevin Bacon problem for movies. Every actor is within 6 degrees of Kevin Bacon. Graphs are very good at solving those sorts of problems. They're also very good at working with heterogeneous data sources, where especially those that have complex relationships. It'd be nice to say that all the data comes in clean and, clean, organized, and ready to be put in, but we all know in reality that's definitely not the case. So graphs are very good at working with disparate data coming in from disparate sources that have a lot of complex relationships that need to be modeled in a way that they can be used. And they're really efficient at being able to work with data that's full of really complex many-to-many type relationships. I tend to think of it as very helpful to think about these sorts of, the difference between a graph and others and some other technologies. It's really the difference between viewing your data as multiple Excel spreadsheets that you're trying to connect together, or in the case of a graph, viewing your data as a mind map tool that lets you think about your data differently. So why use a graph? Now that we've talked a little bit about what graphs are, why would you use them? Well, there's some common business problems that, if you do much investigation or much Googling to try and answer, you tend to run across. Graphs are really great for things like detecting fraud or providing personalized recommendations or building knowledge graphs to, connect siloed data sources together, or connecting, identity, doing identity resolution to try and determine, unique customer identities. Graphs are actually also very good at being able to use as inputs into machine learning algorithms, especially where the problems that you're trying to solve are benefit from the connectedness of the data. So those are really some common graph business problems that get that tend to be, I don't want to say easily identified as graph problems, but ones that people tend to be able to gravitate towards. But there's a lot of other problems that are not so easily recognized. Maybe you need to do a risk analysis of your supply chain or your IT infrastructure, and being able to use how all of the different aspects and components are connected together really will benefit that. So, where are the risks in your IT infrastructure? Or maybe you need to track data lineage and you need to know, where did this data come from? Or you want to be able to find, you have a search type problem, but the search results you're getting don't really relate to the question you asked. They're sort of an answer that's right, but they aren't really giving you the contextual richness that you're looking for. One that when I started with graph databases that kind of surprised me is the whole access and identity management aspect of it. How does person A have access to person B? So most organizations, you'll end up with if you're working with Active Directory or some other permissions management thing, you end up with kind of this complex network of access rights, because this person is in this group that has access to this folder from this time of day to this time of day, sort of thing. And then things like house scenarios, like if what if type things. If I change this price, what is it going to affect downstream of this? So I kind of like to think of it as graphs are really all about solving the when, the why, and the how of your data. Where are the risks? Where did the data come from? Why are my search results not related? How does this person have access? How does this impact downstream things? So I think if you can take away one thing about graphs from this talk today, I think this is really kind of the key piece. When you start to use graphs, and if you have a problem that fits into the where, why, or how of the data you're looking at, a graph might be a good solution. But one thing you notice I haven't necessarily even talked about today is graph databases, or talked about yet is graph databases, because you can use graphs without graph databases. So why would you want to use a graph database? Well, a graph database, graph databases are all about working with highly connected data. And they're they're optimized for working with highly connected data in ways that other technologies aren't. Some of the challenges you tend to run into when you're working with other data technologies, when working with highly connected data, is that they tend to be unnatural for trying to query those relationships about how, especially when you want to answer things about connectedness or paths in data. And this tends to lead to inefficient processing of those sorts of queries, because they're not optimized for that sort of solution. And most other technologies like relational databases have a rigid schema that's inflexible for changing data easily. And it doesn't allow data to evolve very easily without having to do some large scale ETL type process. So how do graphs address some of this? Well, graphs and graph query languages at their very heart are designed to move through data as opposed to create chunks of data. So graph query languages are optimized to move through connections in the network. So in a graph, in this case, we have a graph where, it's representing that Dave works at Amazon. When you're querying this data, you're basically starting at one location, and then you're moving from one location to another location. Compare that to something like a relational database, where relational databases work by combining sets of data. So if I wanted to represent that same thing in a relational type scenario, I would have one table that has a person named Dave, a table that has a company named Amazon, and when I joined these together, I would basically get a bigger table that has a person, a person column and a company column named, so you can see that Dave works at Amazon. The problem with this is not necessarily when you're working, when you're doing a single join, something like this, but when you start to do many joins, or more importantly, an unknown number of joins, this tends to lead to a lot of difficulty, not only in processing efficiently, but also just complexity in your queries. If you've ever had to write manage or use recursive CTEs in any sort of relational database, they tend to be very problematic to make perform well or to maintain, to be honest. So, like I said, graphs are also about efficiently processing how you move through the connections in your data. So let's look at that same example again. Dave works at Amazon. One of the big differences to think about when the underlying way that graphs work and graph data is stored is in a graph database. The connection, the works-at connection that is in this example is actually data itself. So when I need to actually retrieve that connection information, when I need to figure out who Dave works for, all I have to do is retrieve data from the system. In something like a relational database, that works-at connection would be represented by some sort of foreign key across tables. So it's really not data in itself, it's metadata. It's a higher level. So when I need to use that connection, it needs to be calculated in order to be able to actually materialize it out. And the last kind of thing where graph databases tend to work really well is that the schema flexibility. So graph databases in general allow you to add, in many cases, new relationship types, new entity types, new property types without having to go through any sort of explicit schema definition. So sometimes you'll see this you'll see graph databases talked about as being schemaless. I've never been a fan of that term because if your data, if you have data in something, it has schema. It's just whether your schema is explicit in the case of something like a relational database or implicit in the case of something like in some cases, something like a graph database or document databases and there's some others that have that same sort of concept. One of the bonuses of this sort of schema flexibility is they tend to make it easier for people. Graphs tend to be easier for technical or non-technical or new people to come on board and actually understand what they're looking at. If you've ever come into a mature system and tried to actually understand the very complex ERD diagrams that go on, you'll know that takes a lot of time for somebody to kind of sit there and grok in order to understand how to get data out of it. Graphs, because they tend to be a bit more intuitive and they tend to represent things in a closer way to the actual domain, they tend to be a lot easier for people to pick up. But graph use cases are really all, when it kind of boils down to it, graph database use cases really are all about the questions being asked. As I said, they excel at answering questions about like the what, where, where, and what, why, and how about it. What does this person want to buy? Some sort of recommendation engine. How are these people connected in a social network? Or why did, some sort of dependency analysis of why did X impact Y? And these questions are really kind of boil down to, the types of questions that graph databases solve well really boil down to kind of three things. They boil down to questions that are really about navigating a potentially variably connected structure of the data and using that structure to filter or compute a result on the basis of the strength, weight, or quality of those connections or relationships. Or ones that tend to require traversing that unknown number of connections. If I want to find out what is if you have let's say you have an employment hierarchy and you want to find out how you're connected to the CEO. Well, you might be one hop away, you might be 2 hops away, you might be 20 hops away. It kind of depends on the organization and where you sit, but you don't know that ahead of time in your query. So that unknown number of connections is something where graphs tend to excel. But that being said, they don't solve every, they don't solve every question better. There's, relational databases and other database technologies have been out there for a really long time, and they excel at answering specific types of questions, especially ones that are about how much, count these items, find X based on Y. What were the sales for April? give me the total sales for April of 2021, or how many people bought this product in this location, some sort of, faceted search sort of capability. Things of that nature are really ones that graphs, while you can do them in most graph databases, are not really optimized for, because they're not really using the connections in the data to be able to calculate it. So usually there's other technologies that are a better choice. So I kind of like to think of it as graphs are not an island. Graphs are really, a member of the different technology suites of databases out there, and choosing the right database to solve the right problem is really kind of key. And usually that comes down to choosing graphs or other databases in conjunction with, or using graphs and other databases, graph databases and other technologies in conjunction with each other to be able to answer the questions very, very well. Most frequently we obviously see that graphs are used with relational databases. I always like to think about it as, every problem has 100 different questions, or every application has 100 different questions that need to be answered, and relational databases answer 80 or 85 of those really well. Choose the right technology for those other 15 questions versus trying to fit a square peg into a round hole. So we tend to find, in my experience, that other databases are often used to answer the types of questions, whereas there's a distinct answer, a single or a set of distinct answers. Who bought this product? What is the average rating of this movie? What was part of order A? What was part of order B? Something like that. But graphs are really good at giving you answers to questions where there's a range of answers, where there may or may not be an exact right answer. What product is this person likely to buy next? What movie will this person like next? I have a colleague that has used an anecdote in the past that's like, relational databases are really great at telling you how much it would cost to buy everyone in the room a beer. Graph databases are really great at telling you what beer they would like to purchase. So now that we've talked a bit about graph databases, let's talk a bit about, Amazon Neptune, what Amazon Neptune is and why you should use it. So Amazon Neptune is a fast, reliable, fully managed graph database offering provided by AWS that's basically purpose-built to build and run applications over highly connected data sets. The core of Amazon Neptune is a purpose-built, high-performance graph engine that's optimized for storing billions of relationships and querying those relationships with millisecond type latencies. Neptune supports the two most popular graph models out there, those being Property Graph and the W3C's RDF data standard, as well as the respective query languages of Apache Tinkerpop Gremlin for Property Graph and Sparkle for RDF. Both of these query languages are optimized for allowing you to build queries that efficiently navigate highly connected data sets. And this is being used by many customers today to power use cases such as recommendation engines, fraud, knowledge graphs, drug discovery, network security, things of that nature. At its core, as I mentioned, this is a fully managed graph database service. So it comes out of the box as a highly available, service with read replicas, point-in-time recovery, continuous backup, and replication across availability zones. It's secure by default with HTTPS encrypted client connections, as well as encryption at rest. And because it's a fully managed service, you no longer need to worry about a lot of the database management tasks that you may with other traditional database technologies out there, such as hardware provisioning, software patching, setup, configuration, backups, all of those sorts of things. So Neptune was announced in May of 2018, so we're coming up on our third anniversary of being in GA. It's currently available in 21 AWS regions, and it has, if you are in, depending on the domain you work in, we are ISO, HIPPO, SOC, PCI DSS compliant. Going to kind of briefly touch a little bit on kind of Neptune's high-level architecture, just so you kind of understand. Neptune is an instance-based database, so at its core is these instances that run the high-performance graph engine. These we have a single write instance that can be scaled anywhere from a T3 medium up to an R5 24XL. So the write instance allows for vertical scalability. On the read replica side, we actually support both horizontal as well as vertical scaling. So you can scale any of these from a small T3 medium instance for something like a developer workload up to that same R524XL. It's out of the box, it's durable, it's ACID compliant with immediate consistency. But one of the unique aspects of Neptune is because it's a cloud native storage solution or cloud native database, we actually have separated out the compute from the actual storage service. So the storage service is a highly resilient cloud native storage service. When you write data into Neptune, that data is replicated 6 times, twice in each of 3 availability zones. So you basically have a fully redundant system out of the box without having to set any of that up. It's multi-AZ by default. Like I said, it supports encryption at rest, automated backup, and it's actually a consumption-based model. So besides the instance cost of running the different instances, from a storage side, we actually are a consumption model. So you start at 10 gigabyte, you start by paying for 10 gigabyte storage, and then you basically, as you add data, you start to pay more. In 10 the data size starts to grow and you start to end up paying more in 10 gigabyte chunks. So you don't have to know ahead of time, what size disks you need to provision or anything like that. It'll just grow as your data size grows. This all backs, at the very top, this all backs basically what you as application developers are going to work with, which is those endpoints supporting those Gremlin and Sparkle query languages. This is where you use this is where you build an interface with your graphs, your different, identity graphs, fraud graphs, knowledge graph type applications, as well as this is where our Neptune notebooks connect. Neptune notebooks is a set of Jupyter magics that we provide that basically works as an IDE for working with Neptune. In addition to that, we have a set of endpoints that are basically management or administrative type endpoints more than application development. First one being a bulk load endpoint that allows you to load data from S3. Next, we have a stream endpoint. So this is a CDC change stream. So if you have you want to use the changes in your graph to trigger some sort of downstream action to occur, you can use this. We have a set of cluster and instance status endpoints to basically provide you, overall views on the health and status of your cluster, as well as a query explain and profile endpoint that allows you to get a very detailed look at how your queries are running within Neptune. As I said, we support the 2 primary graph models, those being the property graph model with the open source Apache Tinkerpot Gremlin traversal language, and the other one being the RDF framework with the Sparkle. So what are some of the kind of common workloads we see with Neptune? We see a lot of customers building out social network sorts of scenarios where you're trying to find connections between friends or colleagues within the data. Identity graphs. These are all about providing a unified view of a customer by linking devices, IP addresses, and browsing behaviors together. Fraud detection fraud detection is really about finding patterns of transactions within data that potentially link together, a transaction to known fraudulent users. Entitlements, this goes back to that sort of authentication or the authentication and authorization sort of use case where you want to find conditional paths from a person to a resource to see if they have access. Network analysis, this is sort of your if you think about it, these are your tree traversals. If you want to find everything in a supply chain or if your what if analysis, your dependency graph sorts of things. So anytime you kind of want to traverse a tree either top down or bottom up. And last one is the knowledge graphs, which knowledge graphs are all about creating, linking data sets and concepts together to provide a kind of a holistic overview. So actually going to jump right now into some demos. I guess I'll take a pause there. Is there any kind of questions that we need to answer at the moment? If you're talking, Peter, you're on mute.
Yes, I should really know how to work these things, shouldn't I? So comparing graph databases to JSON, if you're sort of fairly new to the graph databases and stuff like that, isn't JSON more useful in case of storing different informations, or why would you use graph over JSON?
Why would you use graph over JSON? So I mean, JSON, I assume you're probably talking about something like a document or a MongoDB or some sort of document type data story would be is where I'm going to at least answer the question as. So something like a JSON or a document database is really great when all you want to do is be able to kind of fetch and retrieve that entity. If you want to try to start linking those entities together, you might be able to do that, kind of in one, a parent child or many parent, or, maybe even two levels of depth there. But if you want to be able to start saying something like, I have this organizational chart where I have many different unknown levels between me and somebody and the other person I want to find. You can think of this as the Facebook example, for lack of a better example. You want to find out how you and somebody else were connected on through Facebook friends or through LinkedIn friends. Trying to do something like that against a document data store tends to not perform very well, especially when you start to scale that out to large sizes of large numbers of entities.
Sounds good. We've got another question from Olga. Are there any design patterns in graph databases? What tools can you recommend to design graph databases? A bit like the NoSQL Workbench. Is there something similar for graph out there?
I mean, there are definitely design patterns for graph databases. The design patterns tend to be very kind of specific to what type of graph you're trying to build out. If you're trying to build in an identity graph, we definitely have design patterns that tend to work best around that. If you're trying to build out a fraud graph, there tends to be general design patterns. Probably don't have it, there isn't kind of a general, here's how you build all graphs, unfortunately. One of the things I would say is, especially if you're going to look at working with graphs or graph databases, the best place to start is to sit down and whiteboard out what your domain model looks like, how you think about the domain, the terminology you use, and then take that with the actual questions you want to answer. And those are kind of the two key pieces that you want to start with to be able to start drawing out start to figure out what the schema of your graph is going to look like. As far as tools, there isn't kind of one tool out there to rule them all. There's quite a few tools out there. If you are in the RDF space, there's tools like Pool Party, Semaphore, things of that nature that will help you build out the ontology, which is basically a really fancy way to say the schema of your RDF database. For property graphs, there's not, because of the more flexible nature of it, there's not necessarily tools that you need to use to explicitly define those sorts of things. So there isn't really kind of one tool I can recommend there.
All good. And just one last question real quick from Keith. What is the biggest mindset shift obstacle for people familiar with other forms of databases when they try to implement graph databases?
Biggest mindset shift and obstacle people have when coming from other databases is it's not about rows and columns. It's about entities and connections, and that is the hardest thing for everyone to for anyone to kind of get over it, myself included. When I started, it was very difficult to kind of make that shift of, I don't have, my data isn't tabular. It's not Excel spreadsheets. It's a mind map. That combine that with the nature of querying, where you're not building out that bigger and bigger table as you go along, and you're really moving from point A to point B to point C. And those two are the biggest obstacles that people have to start. It goes against everything we as developers have been working with for years. So it's definitely a bit of an obstacle that people have to overcome is to break that sort of row and column mindset.
Can imagine. All right. Sounds like you've got some really cool demos to show us. So I might mute my mic again and let you take it away. Okay.
So the first demo I was going to show here is actually, this is based off of a blog post I did last fall. But basically, there is a tool published by Tableau, an open source tool out there published by Tableau called Altimeter. And what Altimeter does is it actually generates a graph of your AWS resources, so you can see how the different things inside your AWS account are actually connected together. So in this case, what we're going to do, I'm not going to walk through all of the details here. If anybody's interested, I can link to them in, we can provide a link in the Slack to the blog post. But really what I'm going to do is, first thing is I'm actually going to run the data. So this is going out. It's actually using the Altimeter tool to scan my AWS account that we're on. So we'll take a look and see what's in there. It takes a moment because it actually goes through and basically generates. So this is not only running through the graph, it's actually not only running through my account and pulling out all the metadata and information, it's actually generating the graph inside Neptune or storing it into Neptune. So, let's start out by taking a moment and looking at what all the data is. So what you'll see here, the query language you're looking at here is Gremlin. This is the query language Neptune supports for property graphs. One thing you'll notice is it's a bit different than what you're probably familiar with coming from a SQL sort of background. This is Gremlin is an imperative style query language. So it's much more like a stream processing language than a kind of a declarative SQL type syntax. So you can come in there, you can see that we have a bunch of different vertices and edges in there. Like I said, I'm not going to go through all of the details here, but this is basically setting up some of the visualization stuff to be able to support. Basically, I'm going to go out and now see what all of my account information looks like when we graph it together. So as you can see, you can start to see the power of how connecting your data together is with this sort of application where you're basically, first off, you're able to see I have a lot of things out here, which I think are probably IAM roles and policies that are not connected to anything. Might be good if I went and cleaned some of those up. But you can see, if you start to kind of come in here to the center, you can start to see how I have subnets or account associated with VPCs, that are tagged together, that are associated with security groups, that are associated with, a variety of different RDS, database type objects. But let's look at this and actually answer some real questions with this data. Maybe you want to see, do I have any publicly available EC2 instances that access my Amazon Neptune? So maybe you need to use this for some sort of security or compliance. It looks like I actually don't have any of those at the moment. But maybe you want to be able to find out if you have EC2 instances that are open, where at least one port is open to the world. I don't have any of those either, but you can kind of start to see the idea of what you can use this sort of information for, to be able to use this graph of your AWS resources to be able to look for things like security violations or compliance issues, things of that nature, or honestly just to see what you actually have in your account. Because if you're anything like me, you probably have a lot of stuff that you didn't even realize you still had in there. So that was kind of one demo I had. The other demo I wanted to sort of show here today is actually another blog post that actually was just recently released. And it's really all about building out applications on top of Neptune. In this case, I combined a couple of different services together to basically take the semi-structured data of a blog post and put it into a knowledge graph to put it into a knowledge graph inside of Neptune, and then to build a chatbot user interface on top of it. So in this case, I'm able to go in and use basically a chatbot component to be able to go and pull some, to perform some natural language processing on top of my data, to be able to pull back some graph information based on the connections. I can pull back things and do some sort of kind of more complex searches here. But when it really starts to get interesting is when I want to start to see how things are connected together. So if I want to see, maybe instead of just seeing what someone's written on something, maybe I want to see if two people have actually worked together on specific applications or on specific blog posts, I should say. you can start to see how this is actually powering and pulling back some of that, those connections and displaying that information. But that's really only scratching the surface of the types of questions that you can answer. So in addition to that blog post, we actually, as part of our Neptune notebooks, we've published out a series of sample applications. One of those applications is a knowledge graph based application, and it's actually based on this same data set. So if you fire up a Neptune notebook, either through the console or by using the open source graph-notebook package available on PyPy, you will get this sort of notebook, and it comes in. It has a variety of different things. It has a variety of different things. It starts with, basically, if you look at it from the very top, what it does is actually provides you an overview with some getting started information that basically shows you how to load this data set into your Neptune cluster. Talks a little bit about setting some of the visualization options that we're going to use to basically display things. And then it talks a little bit about what the data model is. In this specific case, we're building a knowledge graph to basically provide more contextually relevant search results. So in this case, it started out with some semi-structured data from an AWS blog where you had a post, a tag, and the author. This information was actually then run through Amazon Comprehend to pull out additional entities, which kind of gives us a data structure looking more like this. So it starts to get a little bit more interesting and have some more information associated with it. We can then use that to query information. So if we want all of the information about a specific blog post, we'll see it shows up here. This is kind of all of the information about one specific blog post. In this case, it's called How to Get Started with Neptune ML. We can then use that same those connections and that information to start seeing, okay, how did these people, how have these co-authors worked together in the past? Have they worked together in the past? Are there other specific examples of, posts where they have, worked together in as co-authors in the past? So you can start to see how you can use the connectedness in this data to answer questions. Like I said, I'm not going to jump through all of the details here. But one of the other things you can start to do is you can start using these connections to stitch entities together that you didn't necessarily know were connected. You can find things like, what are the most common topics people use? What are the most common topics that co-authors of this specific person use or have written about? What are the most common, in this case, non-Amazon topic that's been used, because there's obviously a lot. And if you want to look at what the actual underlying graph looks like, as you can see, there's a lot of very specific questions in here, and a lot of information about how this data is actually connected together. But one of the things that I tend to find much more interesting is, given this information, I want to find unknown connections in my data. In this case, we're randomly choosing, I want to see how China and Ohio are connected together. So if I run this query, it's going out, it's searching through that knowledge graph, those unknown number of connections that I kind of was referencing earlier. It may be one step away, it may be 20 steps away in order to get that information, and pulling back those relevant connections between China and Ohio, two things that don't necessarily seem like they would be connected together. But as you can see, they are connected together through a couple of different pathways. But this is the sort of thing that a lot of other technologies, for example, trying to do this in a document database, would be very difficult, because you wouldn't know whether it's one hop or two hops or 20 hops to get between the two. Same sort of thing here, but you can also use this to filter out results. So in this case, I'm looking at finding the ways through China and Ohio that don't connect through Wellington, because there's connections that go through Wellington, New Zealand there. And the last thing I kind of wanted to show is you can actually use this sort of information to perform much more complex things. Like, I want to find out how posts that are written by Dave Bechberger also mention Seattle, and being able to visualize those sorts of connections. So that's kind of all I had today. Are there any kind of other last questions we have before I hand it over?
Yeah, just one from Stephen White, just real quick. Can you federate the graph to a relational model for consumption by traditional consumption tools like, business intelligence tools? Like, I'm guessing like a Tableau or something like that.
Currently, there isn't really. There's no direct way to federate to a relational model using something like a JDBC connector or something of that nature to pull into a Tableau or a QuickSight or other tools like that. You'd have to basically. One way we've seen a lot of people work with that sort of thing is actually using the graph to store information and then actually creating essentially read models on the back end that are optimized for the types of BI queries you want to do. Because especially depending on exactly what it is you're trying to show, graphs may not be the most optimal way to pull that data out. You may want to pre-calculate some of that data and store it in some other technology.
Yep, that makes a lot of sense. Well, I think that was a fascinating presentation. Some of those demos were just like, wow, that really blows me away. Especially how you can visualize, like your AWS account infrastructure. I'm sure, like some of the security folks will be like, that could probably help me out. And maybe they're a little bit scared to actually run that tool over some of the production accounts or something like that. But
Potentially, but I mean, I think that's actually what was kind of the main focus when Tableau built that was really trying to ensure security and compliance.
Can imagine. Yeah, that makes a lot of sense. Well, thanks so much, Dave. We'll draw the winner of that for the best question. If you can pick one once you hop off the stream, and then we'll reach out to that person and send them the code. That sounds really good. So thanks.
Okay. Actually, there was one quick last thing I wanted to do. I was going to throw up really quickly I'll have you throw it in the Slack channel. The 35% off code for any Manning product in any format.
That's already been done. So
okay, even better.
It should all work out really well. Round of applause for Dave. Thanks so much. Chat to you later. Awesome. Okay, so we've got Archie Arakkal. I missaid your name earlier, so I do absolutely apologize. Just before we dive in and have a quick little chat, there's a couple of announcements that I wanted to make. So obviously, you've all heard of Yao Data, the amazing data conference coming up. Definitely get yourself a ticket to that one if you haven't already. That's going to be really good fun, and I always look forward to Yao Data conferences. I'm pretty sure like the it's fairly low cost tickets and things like that. So definitely do check out that. AWS Summit is happening in Australia and New Zealand. It's an online event. It is happening on, what is the date? 18th and 19th of May. Definitely worth checking that one out as well. That's just going to be wall to wall, heaps of really good fun talks. I'm doing a bit of a fun talk on Amazon Location Services, which is a really cool sort of new service that they've just announced. So that's going to be good fun. But yeah, there's going to be a ton of really cool content. So definitely worth checking that out. But without further ado, we have Archie Arakkal. How's it going?
It's good. I'm actually so happy that I'm going after Dave because I was literally just stuck watching him the whole time, and it's very relevant to what I'm going to do. So
yeah, so you're going to be taking us through demystifying data and machine learning. You're a practice lead at the Intelligent Data Division at Synthesis Software Technologies. Did I see somewhere that you're doing a PhD through MIT with the topic optimization of transfer learning in multi-agent reinforcement learning? With federated learning techniques in the healthcare sector? That just sounds amazing.
mouthful.
So I'm just feeling slightly intimidated here, but yeah, it's really cool, and it's like when you approached me about speaking at the meetup, you mentioned that in the machine learning space, that data engineering is becoming quite topical. So and it's for us doing data engineering for machine learning, so becoming quite topical. So it's really great to have you here.
Thanks, Peter. Cool. I'm just going to dive straight into it. I think you've given me enough of an intro. So I think we're good.
Do you want to share the slides?
Yeah, just give me a sec. I'll share the right screen. Cool.
Awesome.
Okay.
I will drop off and let you take it away. Thanks.
Great. Thanks, Peter. Cool. Thanks for joining, everyone. I'm actually, like I mentioned earlier, I'm quite happy that I'm going after Dave, because a lot of what I'm going to be talking about is very, very relevant. And I think it'll make it easier to see how there is a direct correlation between machine learning and data. Just a little bit more of an intro around myself. So currently my role is practice lead within at Synthesis. And essentially we are one of the largest partners, AWS partners in the African region. So I do tend to work a lot around the AWS side of things. And essentially a lot of my projects are oriented around AWS services, but that doesn't necessarily mean that that's all machine learning is about. I just wanted to clarify that. Okay, so I'm going to dive straight into it. Just to start off, I actually just wanted to get into a little bit of detail around what AI is, what machine learning is, just high level. It's not going to be a lot of in-depth detail around it. I just wanted to just kind of give you a little bit of a brief introduction into why it's important and how data eventually does feed into the realm of machine learning. Cool. And I had to have a meme because all presentations should have a meme at some point or another. And essentially what I wanted to go around talking about is why AI is important, or AI or machine learning. We tend to alternate between the two, how it can go wrong, how it can be potentially solved for, and how it can go right. So as you can see on the on the images on screen, we tend to give machine learning and AI quite a lot of credit around what could go wrong. The reality is a lot of it is very much dependent on the data you input into your system at the end of the day. So as much as you could say that machine learning and AI will be taking over the world, our machine learning models are only as good as we actually start off at our data side of things. So if the data engineering isn't correct, then we don't have any machine learning to start off with. And how it can go wrong, if it's that's what you're seeing in the diagram on the screen. You could have a 99% accuracy in your model, but if it's not actually a representative data set, then you actually don't have a model that is representing your problem statement. How it can be solved for is exactly the reason why I'm here today, because I feel that we need to put a lot more focus into our data engineering side of things to ensure that we collect data in a clean manner and ensure high levels of data quality before we can actually pump it into any sort of machine learning model. How it can go right, once you do actually have your models fully represented, then by the end of the day, you can actually get into the realm of fraud detection, personalization, everything that Dave was mentioning. We can actually do much better within the machine learning space of things and actually start figuring out new patterns without having to do a lot more work in the data engineering side of things. So that's just very high level as to why AI is important and how we can actually practically use this within our constructs. Yeah, I had to bring this in here because there's a lot of misconception around AI going to be taking over the world, and essentially we tend to go down the opposite direction because we are afraid of what this unknown means. But the reality, like I've mentioned, is if your data is not accurate enough, if your data doesn't represent a good enough data set, you would encounter a similar problem to what you're seeing on the screen. You actually don't have a machine learning model that is representing what you need to do. So in this particular case, a cat is being seen as a dog, which is a very, very direct relationship into understanding that your data is extremely vital and extremely important in building anything in this AI side of things. Cool. So now that I've given you a brief introduction into why data is important in the machine learning side of things and how it can potentially go wrong if your data is not good enough for your model, I'm just going to dive into some of the areas that machine learning tackles around and how that fits into the data engineering side of things. And if I do a good enough job, you will hopefully be able to see how your traditional data engineering work does actually feed into what you're doing. So just a little bit of background into how I actually how my machine learning engineering story has gone about going is I started off as a software engineer. Then I dived into the machine learning space, specialized a little bit more in that realm. And then I realized that we needed to actually sort out our data engineering more than anything else. So majority of my day is 70% data engineering, and close to 30% is literally just the data science and the machine learning component. So it is very much a very huge component of my day job, even though I am a machine learning engineer. So essentially, if there are a lot of data engineers out there and you do want to go into this and specialize into the machine learning world, you're not too far away. Yes, there are some mathematical components to it, but it's just a matter of upskilling in the right domains after that. But data engineering is going to be your foundation at the end of the day. I think it makes you very powerful if you do have a data engineering foundation more than anything else. Cool. So as I mentioned, a big proponent of my life is pretty much around the data space of things. So as you can see, even though we give machine learning a lot of credit in a system, so for example, if you're to have a facial recognition system, you tend to say, oh, this is AI, this is all the artificial intelligence type system. But the reality is the AI component is very, very small in the entire infrastructure. What we actually focus on is, as you can see on the screen, data collection, data verification, automation. So all these other aspects of a system need to be well worked out before we can add any kind of artificial intelligence or machine learning to the mix. So as much as it's great being in the machine learning side of things, it's very, very important that you actually cater for your software engineering practices as well as your data engineering standards before you can actually get a successful product. I mean, yes, you can get a unsuccessful product if you don't focus on those aspects, but if you do want to have a system that works well, you do need to have all these other components around it sorted out as well. And then once you do have all these components around it sorted, which is predominantly software engineering and data engineering, then you can actually bring in a specialist, like a specialist from a data science side of things, or an actuarial scientist, or even a machine learning engineer to come to the table and actually add the extra bit at the end of it. But all of this needs to be sorted out first. I'm just going to talk quickly around all the different technology stacks you have there. And as you can see, a big proponent of machine learning engineering is your data component. So you have your data component, you have your development, deployment. So all of this is, as you can see, it's very, very similar to a standard software engineering practice. But you do have to have your data component as well there. If you don't have that, then you actually don't have anything to work with. So yeah, this is essentially what a typical technology stack would look like. This is not everything. Trust me, there are tons more. There's Dave's little Neptune graph stuff there as well. So essentially, we do have a huge mix of tech stack that we work with in order to get an entire system into production at the end of the day. Okay, so I think this is the point where it'll start making sense as to how data does fit quite well into the machine learning lifecycle. So just to start off, when we're to get a project, we start off with trying to identify what the business problem is. Once we've identified the business problem, we need to kind of frame it into a machine learning context. So what does that mean? Let's take a fraud detection use case, for example. We have a transaction. We have a bunch of transactions coming into a banking environment, and these transactions we were trying to understand whether they are fraudulent transactions or not, because we've received a bunch of complaints, etc. So that's the business problem. How do we frame this into a machine learning problem? Essentially, we would say, cool, our machine learning problem in this case is we want to pick up on any anomalies that have been found in the transactions that have occurred in the past couple of months. We'd like to link it up into different databases to verify whether there is any connections. And this is where Dave's graph databases are very, very useful, because now you can start picking up links between different entities, which is very, very crucial, especially in the fraud detection side of things, because you don't necessarily know what entities could give you a potential fraud until you actually test it out. So having something like a graph database is very, very vital in this sort of instance. Once you've framed it into a machine learning problem, then the first step is obviously data collection and integration. And this is essentially data engineering. Literally, all you do in this case is build the necessary pipelines. You would build your ETL pipelines, or you'd build your database connections as required. You would start cleansing and preparing this. And this is the nightmare of Node, I kid you not, because this is when you realize that all the data is in different siloed environments, and you need to start bringing them all together and start standardizing the data, which is, there's 8 engineers on this meetup, I'm sure, where this is one of the problems we tend to struggle with. And then once you do have standardized all the data and prepare it in a specific way, you need to ensure that it is of a high quality. You don't have messy data involved, because if you do have messy data and data that isn't representative of your problem, that affects your final output at the end of the day. So that data engineering component is basically the whole garbage in, garbage out situation. So we need to ensure that there is no garbage coming in. We need to ensure that the pipelines that have been built are robust enough to sustain the different types of entities that are actually going to be coming in the long run. Once you've actually collected and cleansed your data, then you go into a visualization and analysis step. So what this means is, now that you're almost confident that your data is representative, you need to visualize this data. And this is where, like, you have your BI dashboards, or you would have, even within your Python environment, you would have ways of visualizing the data to start seeing. So you do something called the exploratory data analysis, which is what you do to check what the correlations are between the different data sets. You start looking at what percentage of data is involved, all of those things. You start looking at the different features that are involved. When I say features, all I'm talking about is the different aspects of your data. So the different columns in your data, or you look at the different, different columns in your data, and essentially those are your features. So if we're to go back to the example of the fraud detection use case, you have a transaction. So in your transaction, you would have things like amount, you would have location, you would have time, you would have date, you would have where the transaction, you have location where it occurred. You also have the details of the customer as well. So those are all your different features. So now essentially what you do is, once you've gone through the data visualization and analysis, you start kind of understanding which features are important in solving your problem. So in this particular use case, we can say, for starters, we say amount and location is the most important feature. Once you've actually done that, you start creating a model. So then you take your data set, you remove all the other columns that are not necessary, and you only look at amount and location, for example. It's obviously never just amount and location. There's always tons of different features you need to augment. But you do that, you start training your model, you look at what accuracy you're looking at. When I say accuracy, all I'm saying is, you start, once you've trained your model, you send it through the same set of data, or at least a subset of that data that has been labeled already as fraud, and you try and see how much of a correlation there is between those two data sets. And if you find that there is a 70% accuracy, so 70% of the data has been identified accurately according to a preconceived data set. And once you've got that accuracy feature, once you've got your accuracy rating of your model, then the next step is, obviously you need to see whether because this is quite a hefty process, right? And you need to kind of go back and revisit your framing of your problem to understand whether the business goal has been met. If you only have a 70% accuracy and the fraud detection requires close to a 98%, then you have to go back. You basically go back and you do something called feature augmentation, which is essentially, now you just go and look at other features you can incorporate into your model to get a better prediction. So now, let's say we chose amount and location, but maybe something like understanding where or who the customer is, what type of customer they are. So are they someone that is sitting in the higher band, someone that is sitting in lower band? That could potentially assist in building a better model. So you start playing around with those different features, you go through the model training process again. And once you've done that and you feel you've finally got your 98% accuracy, you go into model deployment and predictions and services and all that stuff, which is actually just spinning up an endpoint to ensure that you have the model accessible in the environment that is necessary. But another component of it, this now leads into the DevOps side of things. So we've gone through data ops and data engineering and everything, and we've gone into machine learning engineering. Now we go into the data ops side of things, which is once you do have your model there, that's not it. You actually need to constantly keep checking your model to ensure that there hasn't been a drift. So for example, when I say drift, I mean your model isn't actually predicting the fraud the way it should be predicting it, even with very known use cases. That does happen. That happens because sometimes your features might become stale over time. This happens especially when you have like marketing campaigns, and you might find that in a specific period that campaign was running, and because that campaign was running, specific features were more important than others. So yeah, then you have to go back and retrain and do the same data collection engineering process again. So as I've described now so far, it is quite an important part of ensuring that you do have a good enough model at the end of the day. The fact that you need to have that data well structured and connected up, and this is also this element would be great for graph databases, because this is very, very important for us to be able to understand how well our data is representing our business problem at the end of the day. So that's why 70% of my job is actually data engineering, because a lot of the times the data sets that we receive is not in that format. It's not in a structured format that we can actually do the entire process seamlessly. We actually need to start from scratch. So pretty much that's the machine learning lifecycle. This is just another way of representing everything that I've just mentioned, but essentially, as you can see, all the yellows, that's all pretty much data engineering. The rest is like small little components, but a big proponent of a machine learning lifecycle is ensuring your data engineering practice, your data engineering is well structured, and then doing some data preparation from there, which is also part of data engineering at the end of the day. Cool. So I've gone through the machine learning lifecycle. Now I unfortunately don't have a cool demo like Dave did, but I am going to be speaking through some of the case studies. And if there's any questions, I'm happy to answer them at the end of the talk. So and this is a very, very interesting project for me. When we got it working, we were so happy. But and this is actually, it was a fraud detection use case. And essentially what we needed to do was be able to infer, we had to infer debit order faults in transactions. So what was happening, there was a cult, I'm going to call it a cult, but there was a bunch of people that actually was fraudulently taking debit orders from customers, and the fact that the debit orders were less than 200 rand in South African terms, they were not able to pick up on those debit order faults, because if you have a debit order for less than 200, you don't require a customer to actually approve a debit order transaction going off their account. So what happened, this group of people essentially targeted a bunch of unknown customers that actually eventually did lose quite a significant amount of money. It ended up becoming close to, there was close to maybe 50 million that was lost as a result of this group of people putting these fraudulent debit orders on people's accounts. So what we were tasked to do was essentially create a fraud detection system to be able to pick out these anomalies. So how this whole process started off was we needed to go through the whole data engineering process. We need to look at transactional information. We needed to start looking at account information. We needed to start looking at, we actually even needed to start creating something called a single view of customer, which is also similar, where we start connecting different siloed institutes together to have a full view as to what the pattern of a person is. And by having that visual, we were able to start picking out features that we needed. So in this particular use case, the feature that we were able to eventually pick out was amount, location, date, and there was one more, amount, location, date, and understanding the type of customer that is targeted, as well as age bracket. That was also a very, very important component of this as well, because the way in which this group was functioning was they targeted only members between 40 and 70, because that's the group of people that actually worked, that actually it affected more than the others. So that was also a very important feature for us as well to look at. And once we actually figured out those features and collected all that data into one location, ensured that we had that single view, we standardized the data. We actually had to go through quite a few iterations, because what we found was, because they were different siloed data sets, a lot of the times data that was representative in one account or one aspect of a customer was not represented in another aspect. So you might have found ID numbers that were not the same in different accounts, but still refer to the same person. So there was like a lot of cleansing that is necessary. And once we got through all of that, which is all data engineering, as well as we actually build the necessary pipeline. So we actually transport all the information into our S3 buckets. We used just a DMS for this particular use case. We just migrated all the data into our S3 bucket. And then we had a CDC pattern just basically picked up any changes from our central single view. And then that was all migrated into S3 bucket. And then we started training our models to start picking up anomalies. So there was 2 different models that we deployed. I'm not going into too much detail about those models, because it was a SageMaker model that was pretty much installed in there. We had to add more. We had to actually customize a little bit more of the model itself, but essentially we trained the model. We got a good enough accuracy. We actually had to go back and redo this to do the same process. But essentially what happened was we actually built out the 2 models that are necessary, and then we had a bit of a champion challenger between the 2 to eventually get the most accurate prediction of the fraud. Then we made those models available to the final fraud detector, which was sitting on the bank itself. And then from there, what we did was, every time that the fraud was detected or fraud was picked up, it was pushed through to our Kinesis data stream, so that we could actually have a real-time visual on what's happening within the fraud detection side of things. Then we hooked that up into our QuickSight dashboard. Eventually, we had to move from QuickSight, into Power BI, because that was the tool that was utilized in that instance, but it's just a matter of removing the one and replacing it with other, and eventually pushing all that information directly into the bank's environment. So they had visibility. As soon as a fraud was detected, then it was visualized in the dashboard, but we also had an action point associated to block and send an email, send an SMS or an email to the customer telling them that, look, this could potentially be a fraud. Are you aware of what this transaction is about, etc. So that actually saved quite a lot of money in the long run. But it is as I've been saying, data engineering was a huge proponent of this in order to get all that data consolidated into one location. Because we had that, and because we were able to also figure out how that single view of a person looked like in a more accurate way than how it was sitting in disparate data sources, we were able to start picking out patterns, which wouldn't have been possible if that data engineering wasn't there to start off with. Then this is just a little bit more detail around the action steps that I mentioned. So once all the data was collected, we also try to run it through Amazon Forecast, just because that's how we go about creating these sort of prototypes. We figure out our custom model versus the work forecast model. It also performed relatively well, but essentially we had to work with a bit of both at the end of the day, because that's what gave us the best results. And yeah, well, as you can see, once everything has gone through, we send out email notifications, we send it through to the different dashboards as can be seen. But yeah, that's essentially how we were able to solve this fraud detection problem. It was very much data engineering focused. I kid you not, the machine learning component of it took maybe a day or 2 to train those models. But majority of the work was sitting in creating that single view of the customer at the end of the day. And once we had that view, we were able to pick out the necessary patterns from there. This is just an example of how we went about doing it. I'm not going to go into too much detail. This is more on the ML ops side of things, which isn't that important. Then I'm just going to quickly go through this mining sector one, which it wasn't an AWS orientated project, but in this particular instance, it looks like a lot of blocks on the screen, but all this is I had to create a self-driving vehicle on the mines. And essentially, a huge proponent of this was being able to stream data from a, this is very, very, very difficult, but we had to stream data from a remote location that didn't necessarily have a good enough internet connection to the central server. And essentially, we used Redis streaming in this particular instance. But the idea is also within this phase, within this phase, you see self-driving vehicles is a huge AI type project. You know, when you see AI and you say self-driving vehicle, you'd assume that a huge proponent of it was machine learning or AI. But in reality, there was a lot of streaming, data streaming involved. I learned a lot about Redis streaming by the end of it. I had to play around with Kafka. I had to play around with Flink. I had to play around with quite a few components of data streaming to eventually figure out what the best approach was. And once that was all set out for me, and I actually built that entire infrastructure, so from the bat, it made a lot of this a lot more easier, because once that streaming interface was there, we were able to actually connect directly into the mines that are sitting underground and understand what's happening from a data perspective. We had to constantly keep seeing what sort of streams were coming in before actually making more informed decisions to the model. It was very, very important to have that set up in place before we could actually retrain our models to understand whether the vehicle is going on track or off track. This is a very interesting one. I don't have the architecture diagram for this. I forgot about it completely. But within the healthcare sector, very, very important project that I had to work on. This was very, very much in the academic space, but which means that we worked with a lot of open source tech here, was being able to start predicting malaria. And once again, as you can see on the screen, we had quite a few different data sets that we need to consolidate in order to finally figure out what the best approach was. And essentially, because we were able to consolidate, so there was a Twitter streaming element, because Twitter was also one of the features we eventually had to pull into the mix to figure out where malaria could potentially be isolated. And that was a streaming component that we had to bring in. We had to bring in that streaming component. We had to bring in RDS databases into the instance. We brought in more NoSQL DBs, which is KCDC. So we consolidated all these different disparate data sets eventually, and standardized all of that into one final output, and then trained models based off that. This is also, once again, a very, very much, once we had that sorted out, the machine learning was so much more easier from there. So I think it's kind of important for me, just as part of my journey, and these are just the 3 projects that I've shown that I think is very important, but a huge, some of the lessons that I've learned as part of this journey is, you know, as much as, you know, we have machine learning and AI, it's always important to augment employees into your system, because it's twofold. One is we need to be ahead of the curve when it comes to utilizing machine learning and AI. And if we're not ahead of the curve, then we're not going to be able to utilize AI in the most progressive way possible. And secondly, we have to also think about our systems as it is. You know, there is quite a lot of data engineering focus in our systems. We need to actually shape that up and make it better. We have our software engineering practices. We need to make that better as well. And only once we do actually bring all of those existing infrastructure, existing participants to the group of creating this new project, only then will we actually have a good system at the end of the day. Another very, very difficult pull for me to swallow was that early AI projects do fail. And a lot of the reasons why it does fail is because, one, it could be that the organization is not ready. And 2, it could be that your data isn't representative enough. And this is why, and the reason why data isn't representative, could be many-fold. It could be that you don't necessarily have the best data engineering practices in place to ensure that you have high qualities of data. You don't have any data. I've seen this where you actually don't have any sort of data infrastructure in place to ensure that you've been collecting the data that you need to eventually get to the next step of building a machine learning project. Yeah, so it's quite possible. So once you do, so a lot of the time what I've seen is people go down the route of trying to create a machine learning project or AI project. They realize that their data infrastructure isn't sorted, and that becomes the boost for the infrastructure to actually be fixed from there on, and then only do you get into that realm. Yeah, and then I think just in general, it's important to understand what's out there from an AI perspective, because it is here. It is here, and we do need to still be aware of what's coming up in order to ensure we do incorporate that as part of our current infrastructure. Because if we don't, then we're going to go down the same siloed route of data engineers sit by themselves, DevOps guys sit by themselves, software engineers sit by themselves. So it's kind of important to incorporate. And I think AI could be the one thing that sort of brings all these entities together. Focus on data engineering, and hence why I'm here also, because this is a very, very important component of any sort of AI or machine learning project. And yeah, and then the last few is just about understanding AI ethics and ensuring that we're doing projects in the most in the correct manner, and always incorporating ethics as part of the process, and to focus on more operational and organizational changes as opposed to actually looking at outcomes out of a project, which is very, very counterintuitive to the way we've been doing things. We tend to, when we're building a software project, we tend to ensure that we have all these outcomes. I mean, it is very waterfall, but even in the agile methodology, we do have our ways of working and ensuring that there is some sort of delivery. When it comes to an AI project, it's more about, yes, there is delivery, but at the same time, there's also soft outcomes to ensure that your organization is ready. So bringing in your data engineers, bringing in your software engineers, bringing in your cloud engineers to the mix, and ensuring that there is a seamless way of working with each other. So yeah, that's basically all I have on my end. Are there any questions?
There are. Let me bring one up from Keith. He's asked, yeah. Keith has asked, when it comes to healthcare data, where does synthetic data generation fit into your ML workflow?
Right at the beginning. So right at the beginning. And essentially, it's a very, very important question, because what we're finding in the healthcare space in specific, there is obviously a lot of security constraints. There's obviously, we can't touch this data set, we can't do this data set. So a lot of the times what we do need to work with is metadata, and not necessarily the most representative data sets either. We would get like maybe a small little component of it, and then we try and mimic what could potentially be in the long run. So in healthcare data in specific, we do work with synthetic data quite often.
Yeah, fair enough. That's cool. It's first I've heard of the term synthetic data, so I'll have to do a little bit of reading up on that one. I asked the question in the chat myself, including a few typos, but if I'll read out what I actually meant to write. So you mentioned that you're using cloud provided APIs, or machine learning APIs like Amazon Forecast and things like that, and it's often the case that they're quite powerful. Should we always look to build our own machine learning APIs, or should we leverage the cloud's ready-made APIs?
Yeah, that's a very good question, because, and actually one of my colleagues and I were having a discussion. We actually have quite a lot of things out there already. There's a lot of cloud related APIs. I mean, App Forecast, the Comprehends, you get GPT-3 even these days. There's just so many different types of machine learning APIs that already exist and have been worked on quite extensively. So there is quite a lot of knowledge that is baked into it. So I think traditionally the approach that I follow is I start off with using a cloud-based API, just to see, like, based just high level, how well does it perform? How does it actually solve the business problem? And similar to my machine learning lifecycle, go through the iteration, see how well it's doing, see if the business problem is met, and then if need be, go into custom. So I tend to go down custom only if it's really needed, because why do work if you don't need to, right? So it's that's that approach.
Yeah, that's really cool. I guess it's a great way to bootstrap, just get something out the door really fast, even if
Yeah.
it's, yeah, Sounds really cool. We've got another question from author one. Hey Archie, in terms of data ops, how have you handled model retraining? I imagine these projects will be in use for a while. How have you planned out retraining?
Yeah. Also, it's like, I mean, it is part of the machine learning lifecycle. We need to, so what we do is a lot of the times we work quite closely with the DevOps guys. So in Kubernetes, so one of the projects that I've worked on where we had to do model retraining was in the Kubernetes land. So we essentially built a Kubeflow network to actually put a model into production and then actually pick up on drifts. And how we handle retraining was actually retraining the model. So we went through the entire process. Once a drift was detected, then we restarted the data engineering life cycle again, which was very, very difficult. Something I am looking at, and I'm hoping to actually deploy this into a lot of the instances, is on online retraining. So how this works is, I'm using Kafka for this in particular, but how this works is being able to pick up on drifts, and you essentially pick up on these drifts real time these days. It's got quite beneficial in that regard. So once you do pick up on these drifts, you automatically can update parameters. It hasn't gotten to a point where we can update all parameters without retraining a model. But what we're trying to do is now we can actually get models, update parameters on the fly, and then basically check if the drift has been fixed. If the drift has been fixed, then there's no need to retrain a model. If it doesn't get fixed, then we need to retrain a model and go through the whole data engineering cycle process again. So yeah, it's a good question.
Yeah, awesome. Well, it's been an absolute pleasure having you present here. Really got a lot out of your insights. It's great to actually, go through those case studies and capture all of the learnings because I guess, when you're working, on lots of data engineering problems at a particular company, sometimes, the types of machine learning you get exposed to isn't as varied sometimes. So I think we got a lot out of that presentation. So thank you so much.
Thanks for having me.
Awesome. Yeah, DataEng Bytes, there's a call for papers on at the moment. So, maybe have a think about, dropping in a presentation there if you like, Archie. Thanks so much. Awesome. Just to wrap up the meetup. Thanks so much for all your questions. Thanks to Dave and Archie for their awesome talks. I really got a lot out of them personally. Just a quick reminder, there's YAL data coming up. There is AWS ANZ Summit coming up. So definitely take a look at those. We're actually going to start having face-to-face meetups again very, very soon. You'll be surprised at how soon I will announce them very shortly. We've got something lined up for Sydney and Melbourne at the moment, and we will be actively working on Brisbane as well. So stay tuned for those announcements. Really enjoying all of the great sort of questions and chat that's coming through from this community. It's really a great community to be a part of. We have a blog post competition happening on our Slack group. So if you'd like to write a blog on anything to do with data engineering, we're going to score newbie blog posts just the same as people that have been writing blogs for years and years. So if you'd like to throw your hat in the ring, there is a very cool Lego space station to win and a $50 AWS credit. So that's well worth getting involved in. It's going to be drawn at the end of the month. So yeah, you've still got a little bit of time to get in there. So awesome. Well, ciao for now. Thanks so much again. And we will see you potentially face to face next time, but we will continue doing the live streams, streaming it out onto the interwebs. So thanks once again. Chat to you later. Bye.